a book, and contributes to Forbes.com and other blogs. Each presenter will speak for 5 minutes, after which we will open the panel to live audience for questions. With that, let's begin. We'll start with Yole's Simone Bertolazzi.
Hello, this is Simone Bertolazzi. I'm a technology and market analyst at Yole Development. Yole is a technology and market research company based in Lyon in France, and we have analysts all around the world covering a broad spectrum of thematics within the semiconductor industry, including memory technologies and related markets, in particular NAND and DRAM, but also a number of different types of emerging and volatile memories, including 3D cross-point, or more in general, phase-change memory, resistive RAM, magnetoresistive RAM, and also ferroelectric memories and other types of devices. I would like to start this presentation for the panel by outlining the position of Yole regarding emerging and volatile memories and their potential for replacing flash in different applications. Of course, when we discuss about this topic, we need to distinguish two very different application spaces, embedded and standalone. In the embedded case, where the memory is integrated within the die in a more complex circuit, there is consensus nowadays in the industry regarding the fact that 28-22 nanometer could be the last technology node for embedded flash. And this is mainly due to economical barriers rather than technical limitations. And therefore, there are significant opportunities for new memories for being adopted at nodes beyond 28-22 nanometers, in particular in system on chips or ASIC type of products, or in microcontrollers. And in fact, nowadays we have a number of large players, IDM as well as foundries, that are all active in developing new types of embedded memories for nodes at 28, 22 and beyond. In particular, MRAM is being utilized for its low power consumption in microcontrollers and system on chips, and nowadays we have the first products hitting the market. So in the embedded space, there's definitely a good opportunity for new memories for taking the place of eFlash at nodes beyond 28 and 22. In the standalone business, new memories need to compete with very well-established technologies like 3D NAND for storage type of applications. So at Yole, we do believe that new memories won't replace flash in the next decade. Flash will continue its scaling. So recently, we have been working on a new report dedicated to equipment and materials for 3D NAND manufacturing. And based on this analysis, we believe that it will be possible for 3D NAND to keep scaling in density and cost beyond 2025 and for more than 400 layers. These will be achieved by string stacking approach. Although we are aware that challenges are increasing, in particular in terms of etching, deposition, as well as metrology. New memories in general provide significant technical advantages for certain applications and over existing technologies, but in order to be competitive, they really need to keep improving in terms of density as well as in terms of bit cost that need to be reduced. So as you can see here, we have different types of emerging and volatile memory technologies providing advantages in terms, for instance, of speed and endurance, as in the case of the STT-MRAM technology. Although we believe that by 2025, certain memory technologies will not be price and density competitive versus existing solution. STT-MRAM will be approaching the price and density position of NOR flash, and therefore can be utilized for certain data and code storage applications, and will be starting to tackle the NOR flash market. But it will be very challenging for STT-MRAM to be competitive against DRAM or other types of technologies. It will be 3D cross-point that by maintaining an intermediate price and density position between NAND and DRAM can be utilized for certain applications, particularly in data centers, such as, for instance, real-time analytics, where a large amount of data needs to be stored within the memory and accessed very quickly. So persistent memory and low latency drives in data centers based on phase change memory will be the main drivers for the market growth till 2025. In particular, the emerging non-volatile memory market is expected to grow up to $4 billion by 2025, $4 billion, driven by 3D cross-point and low latency and persistent memory applications, in particularly thanks to the persistent memory modules by Intel that are taking off in the data center space. I would like to conclude by mentioning that we expect that the emerging memory market, despite its growing, it will remain below 3% of the overall standalone memory market, because NAND and DRAM will keep scaling in the future and will maintain their leading position for a number of applications. And with this, I would like to conclude my presentation. Thank you all for your attention, and I will I'm looking forward for the discussion. Thank you very much.
Thanks, Simone. Next, we'll hear from Jongdong Cho of Tech Insights. Jongdong?
Hello, everyone. I'm Jongdong Cho from Tech Insights. Tech Insights is the #1 reverse engineering company in the world, and we provide the world's largest database of reverse engineering analysis of semiconductor and consumer products. Today, I'll present briefly the 3D NAND technology, and then we'll discuss together with you after the panel's presentations. 3D NAND flash roadmap on this slide shows all the activities on 3D NAND. So major players like Samsung, Kioxia, Western Digital Company, Micron, Intel, and SK Hynix, and YMTC, they are all eager to prepare the next generation on and on. So this year and next year, we can see all the 128 layers and 160 something or 176 something on this field. So you can see the Samsung 128 layer 3D NAND and also SK Hynix 128 layers, so-called the 4D PUC NAND on this slide. So we just know that SK Hynix and Intel merged together by the end of 2025. So a lot of activities are there on 3D NAND. All the 3D NAND buildings and height you can see from this slide. So especially the Samsung's 128 layer and SK Hynix 120 layer just revealed on the market. And we see that the height from the source plate to the B9s already up to reached up to 8 micrometer or more than 8 micrometer. It's amazing. So 3D bit density trend increased on and on, including the SK Hynix, for example, 128 layer TLC device. But from TLC device, it already reached to more than 8 gigabyte per millimeter scale. But after 150 layers, such as 176 or 240 layers next year and the following year, probably the TLC bit density increase dramatically. From the die density and the number of NAND layers, like this one, from our expectations. So nowadays, you can refer to the logic device node L7 or L5 nowadays, but stack tiers and DEX or QLC level devices, we can see that for the 128 something layers. But after 5 years, PLC, OLC, or even the stack dies, including the TSV, such as the HBM, likely structures, you can see that. And then after a decade, probably we can see another stacks, like stack packages, PO, something like that. So we can see the trend of the die size. For example, 256 gigabit dies from Samsung, 48 layer, 64 layer, 92 layer, 128 layer, shrink and scale down on and on. How about the 500 layers? It's very tiny die will be there. And currently we can see the 147 total gates, such as the PUC, 3D NAND from SK Hynix, but after 7 or 8 years, probably we can see 500 total gates for 3D NAND applications. So all the major players shows the different cell architectures, such as the VNAND, Samsung, Big Structure, Kioxia Western Company, Intel Micron, CUA, floating gate structure, and SK Hynix, PBIC structure, and then PUC structure. And also, we can see the 96-layer QLC die floor plan like this one with a very higher array efficiency due to the CUA structure. But YMTC has the same concept with the CUA and the PUC, so peripheral circuits under the array. But recently we found 136 total gates from Samsung, and there's also as high as 147 total gates. So how about the China NAND? For example, YMTC 3D stacking applications. The security USB applications, we can find YMTC 32 layers and 64 layers. And Gloway Pro SSD applications and YMTC 500 gigabyte and also the 1 terabyte SSD, you can find the 64 layer stacking structure. About the emerging memory, actually all the emerging memory such as the STT-M RAM, cross-point memory, PC RAM, the RDRAM or CBRAM or FVRAM, a lot of devices and types are there, but cross-point memory, especially cross-point memory, we have been we are waiting for the Gen 2 stack, but probably they would be the 4 stack, but after that, after 5 years or after 10 years, probably that they need another prototype for the higher density on emerging memory side. So a lot of activities from STT-MRAM, cross-point memory, and RDRAMs are there, including all the major players on this area. So we'll discuss more on this after the panel presentations. Thank you.
That's really something. Finally, Tom Coughlin will speak, after which we will open the floor to questions. Tom?
Hello, I'm Tom Coughlin. I'm president of Coughlin Associates. I've been working in the digital storage industry for over 40 years. And in the last 20 years, I've been working as a consultant with my own company, Coughlin Associates. I do various sorts of technical, market, and other types of consulting work. And I also have put on and organized several conferences over the years, including the Storage Visions Conference, the Creative Storage Conference. I've put on and organized other events, and I've also been general chair of the Flash Memory Summit for 10 years. And today, I'm glad to be talking at the 2020 Flash Memory Summit about emerging memories use, why it's growing, and how that's driving capital equipment demand. And this basically follows along another one of the things that I do in my consulting, which is reports on digital storage technologies and their applications. So emerging persistent memories are necessary for development of continued scaling of our technologies, because flash can't scale with process advances, neither NAND flash nor NOR flash. They both are limited at 15 and 28 nanometers respectively. In addition, SRAM scaling may stop at 14 nanometers. DRAM, another popular volatile memory technology, requires continuous refreshes of data, which uses power. So it's not very good in power-restricted environments. But on the other hand, standalone persistent memory applications are growing at the data center, in industry, and in consumer devices. And in particular, low-power, high-density memory is needed for embedded applications. So let's take a look at some of these emerging memory technologies and how they're being used today. Everspin is a company that makes MRAM chips. They've shipped over 120 million standalone MRAM chips. They've partnered with Global Foundries, which makes 300 millimeter wafers, both for Everspin's use, as well as for Global Foundries' work to develop targeted memory applications with MRAM. And all the major foundries, TSMC, Samsung, and many others, are starting to ship spin tunnel torque MRAM products. Phase change memory is another technology that's currently in fairly wide use. Intel's Optane technology is available now in NVMe SSDs, as well as in DIMM-based products. Those have been shipping in fairly good volumes and increasing volumes over the last couple of years. And both products are now in use in storage systems and tied to the next generation of Intel server technology. Embedded MRAM, or MRAM in general, saves power while reducing chip size and cost. It can shrink smaller than SRAM and flash, as shown here. And it also could replace embedded SRAM and NOR since it offers lower power, lower cost, and higher density. And you can trade off various characteristics of MRAM for a particular design, including data retention, endurance, and capacity. Microcontrollers, ASICs, and other system-on-chips will lead in the use of persistent memory in embedded applications. Their need for a NOR replacement has driven major foundries, like I mentioned before, to look at using MRAM and also resistive RAM to replace stalled NOR technology, as well as MRAM to replace static random access memory. One of TSMC's customers, Ambiq, is developing chips that will enable the next generation of battery-powered, always-on, voice recognition IoT endpoint devices. Their fourth-generation Apollo SoC family sets new standards for ultra-low power intelligent endpoint devices by using MRAM memory. The figure shown here is a block diagram of this chip, showing various features that includes, as you can see in the lower left, 2 megabytes of MRAM. Foundries will drive the use of persistent memory technologies, rendering them attractive, increasing the volume, and lowering the total cost of the product, which will eventually replace slower SRAM, and over time, SRAM and upper-level caches. This is from a report that Jim Handy and I recently published called Emerging Memories Find Their Direction. The total emerging memory market, MRAM plus Studio Crosspoint, could exceed $36 billion by 2030. This chart shows the petabyte shipment growth that will drive that number. The assumptions behind this chart for MRAM are that it replaces most SoC, NOR, and SRAM, and has a strong appeal for AI applications. So we show 3D Crosspoint and MRAM, compare them to NAND and DRAM. Development of and manufacturing of MRAM is going to require new capital spending on equipment that is specialized for the manufacturer, and we project that by 2030, there could be $700 million in additional semiconductor equipment that will be spent in order to make these MRAM products. So much of the information in this presentation is drawn from our report on emerging memories, and it's available for purchase. It describes the entire emerging memory ecosystem, the technologies, companies, markets, support requirements, and includes embedded memory and discrete memory. 201 pages with 31 tables and 142 figures, and you can see the URLs at the bottom of the slide to learn more. So with that, I'd like to thank you very much, and we look forward to discussion.
Okay, we're open up for questions now. So anybody who's got some questions for Tom Coughlin or Jungdong Cho, please go ahead and enter them in. Simone, it's like 1 a.m. I think in France right now, and so he's gone. He wasn't able to stay for the question and answer session, but we're very open to getting questions from other people. Let me just take a check here and see.
I think he said that he would answer questions, afterwards, though.
Yes. If questions are emailed into the Flash Memory Summit, then he'd be able to answer them then. So Jungdong, you talked about 500 layers, and it seems like in the keynote today, from Western Digital that Siva Sivaram was talking about even going past that. Do you know of any limit as to how many layers can be put on 3D NAND? Because I know that a long time ago, SanDisk was saying that there would only be 3 generations of 3D NAND, and then they'd have to go to resistive RAM. Now it looks like maybe NAND will stay ahead of all of these new memory technologies. What can you tell us about the direction that might go?
Yeah, so almost a decade ago, we thought that emerging memories could be replace the DRAM and also the NAND flash device at the time. But nowadays, even just yesterday, Micron announced that the 176 layers products already shipped for some vendors. So it's amazing. And also all the three major players, four major players like Kioxia, SK Hynix, Samsung, and Microns, they are eager to develop, and it's kind of a race on this area to increase the number of layers. And all the major players had their roadmaps more than 500. Even in the long term, they have 800 layers on 3D NAND. It's amazing. So after a decade, probably we can see the NAND, 3D NAND, more than emerging memories. So that's my opinion. And that is because of a lot of the 5-bit cells, and also the combined packaging technology, advanced packaging technology, and also the very accurate or very worldwide the package technologies and the solution technologies to make to extend all the NAND array areas, NAND technology extension. So that's why probably I think the emerging memories could not replace the NAND or even DRAM for a while. But anyway, we know that the emerging memories, their STT-MRAM or cross-pointing memory, they have their own advantages, even the reliabilities and high reliabilities and something like that. So maybe they can combine together with a NAND flash device or DRAM device to make some kind of high-end edge solutions in this area. I think so.
Yeah, that's probably way out in the longer term. But I know that you're probably looking forward to being able to get one of those Micron 176 layer things to be able to tear apart. So we'll look for a report from Tech Insights on that.
Yeah, absolutely.
Yeah, we've got a question in here. I'm just going to read it. It says, in the IRDS NAND roadmap chart, the industry is predicted to stay at 176 to 192 layers in 2021 to 2026. Do you think that's too conservative? If you agree with IRDS, what's holding the industry back from going to 300 plus layers? Jiangdong, that,
Yeah.
pretty much
Yeah,
a question for you.
Yeah. The IRDS roadmap predictions are based on their meeting this year, but yeah, I also agree on these questions because they are very conservative, because 176 already revealed on the market, and also the Samsung already already in developed statement they have the 176, and also SK Hynix also has the 176 on the development state. So maybe next year we'll see all the 176, something like that. And then by the end of next year, probably we can see the prototype of the 230 something or 240 something. So although the IRDS NAND roadmap is very conservative, but probably we can see more higher the number of layers next year and the following year.
Yeah, I was just recently, somebody reminded me that in the Flash Memory Summit, I think it was 2015, I was interviewing a gentleman from SK Hynix up on the main stage, who said that they didn't know of any limit as to how many strings could be stacked, string stacking. And so I wrote a blog post. It was called Limitless Layers of 3D NAND. Tom, you haven't answered a question yet, so I'm going to throw one your way, and that is, this 3D NAND technology has also been used for non-NAND technologies, hasn't it? The approach of doing that?
Yeah, there's a number of these emerging memories that are looking at stacking cells, in particular a number of the resistive RAM technologies. The secret is in the selector technology, or being able to control where the leakage currents go to. It looks like there's multiple layers can be created using these technologies, which will allow denser emerging memories as well.
Yeah, I think that also IMEC did a ferroelectric 3D, didn't they?
Yes, yes, they did. Ferroelectric technology is another one that could be done 3D stacking. MRAM, maybe. It's a little bit further out. And then, of course, 3D Crosspoint is a 3D structure. You know, albeit it's not very high now, but it is. But it is built in 3 dimensions.
Yeah, it's just different from NAND.
And there's a question for you in the question queue there.
Oh yeah, I saw that. I didn't know if you were looking at that. So I didn't mention that the first question was from Charles Shi. I've got Suresh Bashkaran. I hope I haven't ruined your name. Who asked from a cache standpoint. He says currently the common architecture seems to be a large NAND storage with cache as SRAM. Will the SRAM for the cache continue? I mean storage cache, not CPU cache. Actually, in storage arrays, the hierarchy, the caching that's used in SANs is usually a DRAM. It's just basically it's a modified server where a lot of the DRAM is used as a staging area before stuff is pushed off into the SSDs. So I don't imagine that will change because DRAM is going to continue to be one of the cheapest memories, you know, the second cheapest memory after NAND flash for a long time. So that'll probably stay in the same place. Zhang, we didn't ask you about DRAM, but I know that you're a really good expert in that too. And do you have any ideas about how much longer we're going to have DRAM before it runs out and, you know, before some other technology like MRAM might be able to take its place?
Yeah, as you know, DRAM process and the integration are so cheap than any other devices. Even the embedded DRAM also use the CPU or even question. Yeah, he said the storage and cache, but even for the CPU cache or controller cache, Intel and IBM, they use the embedded DRAM, not the others. So embedded DRAM still use that, and also the embedded flash, eFlash or eNOA used for the cache area still. But I think that is DRAM process is quite unique and matured and very cheapest one in the world among the device. So that's why for a long time, I expected that DRAM still used on that area, not the other emerging memories. Yeah.
Okay, well, good. Yeah, it's interesting how this is all going because DRAM and NAND flash have stuck around for a lot longer than anybody expected.
Yeah.
I think we're out of time here. I know that I'm just going to recommend for people, you know, to look into both Coughlin Associates and Tech Insights for reports on emerging memories and on existing memories that are, you know, the latest technology. So thank you both for joining this talk. And thank you to our viewers for posting the questions. This has been a very interesting discussion.
Thank you, Jim, for being the
Thank
moderator.
you, Jim, and thank you, guys.
Yes. Okay, good evening.
Bye.
Bye.